Hello there, and welcome to the Cozy Curiosity channel. Tonight, we journey into the ancient world beneath our feet, a world of stone and fire, pressure and time. Geology is the language of the earth itself, written in layers of rock that stretch back billions of years. From the crystals hidden in mountain caves to the slow drift of continents, from volcanic eruptions that shape islands to fossils that whisper of vanished worlds. Geology tells the story of our planet's long and patient transformation. Some of what you hear tonight may surprise you. Other facts might drift past like sediment settling on a riverbed, gentle and unhurried. If this kind of peaceful wonder brings you calm or sparks your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. And let me know in the comments where you are in the world and what time it is for you. It's always fascinating to hear where everyone is listening from. But for now, settle in. Let your breathing slow. Let the weight of the day dissolve like salt in warm water. Tonight, we explore the deep time of stone, the poetry written in granite and limestone, the silent stories carved into the bones of the world. Let's begin. The Earth's crust is just a thin skin on a molten planet. Beneath the solid ground you stand on lies a world of liquid rock and immense heat. The Earth's crust, the outermost layer where all life exists, is remarkably thin compared to the planet's total size. On continents, it averages about 30 kilometers thick. Under the oceans, it can be as thin as 5 kilometers. If Earth were an apple, the crust would be thinner than its skin. Below this fragile shell lies the mantle, a thick layer of semi-molten rock that flows like honey over geological time. Deeper still is the outer core, liquid iron swirling in currents that generate Earth's magnetic field. And at the very center, a solid inner core as hot as the surface of the sun. Everything we see, every mountain, every valley, every grain of sand exists on this delicate outer layer. We live on a thin raft floating above an ocean of fire. The ground feels solid, but it is only the coolest breath of a planet still molten at heart. Rocks are constantly being recycled through the rock cycle. Nothing on Earth is truly permanent, not even stone. Rocks are born, broken down, and reborn in an endless cycle that has continued for billions of years. Igneous rocks form when molten magma cools and solidifies, either deep underground or on the surface after a volcanic eruption. Over time, wind, water, and ice break these rocks into smaller pieces. These fragments are carried by rivers and deposited in layers, eventually compressing into sedimentary rocks like sandstone and shale. When sedimentary or igneous rocks are buried deep beneath the surface and subjected to intense heat and pressure, they transform into metamorphic rocks, their minerals recrystallizing into new forms. Marble was once limestone, slate was once shale. And if these metamorphic rocks are pushed deep enough, they melt entirely, becoming magma once again. The cycle begins anew. Every rock you hold has been something else before, and will be something else again. Stone is not fixed. It is only pausing between transformations. Some rocks are older than the oldest fossils. Long before life left its first traces in stone, the Earth was already ancient. The oldest rocks ever discovered are over 4 billion years old, found in remote regions of Canada and Australia. These stones formed when the planet was young and inhospitable, a world of volcanic violence and meteor impacts. No plants grew, no animals crawled. Yet even then, rocks were forming, layer upon layer, preserving a record of conditions we can barely imagine. These ancient stones contain zircon crystals, tiny time capsules that have survived every upheaval since. By studying them, geologists can glimpse the infant Earth, its early oceans, its first continents. To hold one of these rocks is to touch something older than life itself. They are the silent witnesses to a world before memory, before breath, before even the first whisper of biology. The Grand Canyon reveals nearly 2 billion years of Earth's history. Stand at the rim of the Grand Canyon, and you are looking into deep time. The layers of rock exposed in its walls tell a story that stretches back almost 2 billion years. Each stripe of color represents a different period, a different environment, a different chapter in Earth's autobiography. At the bottom, dark metamorphic rocks form deep underground when North America was still being assembled. Above them, sedimentary layers show ancient seas advancing and retreating, deserts spreading and vanishing, life beginning to flourish. The topmost layers are much younger, deposited when dinosaurs roamed and shallow seas covered the region. The Colorado River carved through all of this in just a few million years, a geological blink of an eye. What took billions of years to build was sliced open by water, flowing patiently downward. The canyon is a library of stone, each layer a page, each fossil a footnote. To descend into it is to travel backward through time itself. Diamonds form over 100 miles beneath the Earth's surface. Deep in the mantle, where pressures are immense and temperatures soar, carbon atoms are squeezed into the hardest natural substance on Earth, diamond. These crystals form slowly, over billions of years, in conditions no human could survive. They would remain hidden forever, if not for rare volcanic eruptions that shoot upward at incredible speeds, carrying fragments of the deep mantle with them. These eruptions, called kimberlite pipes, blast through the crust and bring diamonds to the surface in a matter of hours. Most diamonds are far older than the rocks that contain them. Some are over 3 billion years old, formed when Earth was still young. To wear a diamond is to carry a fragment of the deep Earth, a piece of the planet's hidden heart, brought into the light by fire and violence. It is a reminder that beauty often comes from pressure, and that what seems eternal was forged in unimaginable extremes. Fossils are formed when organisms are buried quickly, and minerals replace their tissues. A fossil is not the creature itself, but a stone memory of its shape. When an organism dies and is buried rapidly, usually by sediment in water or volcanic ash, it is protected from decay. Over thousands or millions of years, minerals dissolved in groundwater seep into the tissues, replacing organic material molecule by molecule. Bone becomes stone. Shell becomes rock. Sometimes even soft tissues like skin or feathers leave faint impressions in the surrounding sediment. The result is a perfect replica, preserved in mineral form. Fossils are fragile, windows into lost worlds. They tell us what ancient seas contained, what forests once grew, what creatures walked the earth long before humans appeared. Each one is rare. Most organisms decay completely, leaving no trace. Only a tiny fraction ever become fossils. To find one is to recover a message sent across unimaginable stretches of time, written in stone and waiting patiently to be read. The Himalayas contain fossils of ancient sea creatures. High in the Himalayas, far from any ocean, climbers sometimes find the fossils of sea lilies, ammonites, and marine shells embedded in the rock. These mountains, the tallest on Earth, were once the floor of an ancient ocean called the Tethys Sea. When the Indian tectonic plate collided with Asia around 50 million years ago, the seabed was crumpled and pushed upward, lifting layers of limestone filled with the remains of creatures that once drifted in warm, shallow waters. Now they rest in stone, at altitudes where the air is thin and the cold is absolute. It is one of geology's most poetic ironies. The highest peaks on the planet were born from the lowest depths. The fossils are proof that mountains are not eternal. They are only the current shape of something that was once entirely different. The ocean floor became the roof of the world, and deep within the rock, the sea remembers. Plate tectonics explains why continents drift across the globe. For most of human history, continents seemed fixed and immovable. But in the early 20th century, scientists began to notice something strange. The coastlines of South America and Africa fit together like puzzle pieces. Fossils of identical species were found on both sides of the Atlantic. Rocks of the same age and type lined up across ocean basins. The evidence pointed to a startling conclusion. Continents move. This movement is driven by plate tectonics, the slow shifting of massive slabs of Earth's crust atop the semi-molten mantle. Below, plates collide, forming mountains. They pull apart, creating ocean basins. They slide past one another, triggering earthquakes. This process has been reshaping the planet for billions of years. Continents that are now separated were once joined. Pangaea, a supercontinent that existed 300 million years ago, eventually broke apart, its fragments drifting to their current positions. The movement continues today, inch by inch, year by year. The map of Earth is not fixed. It is only a snapshot of a world in constant patient motion. Magma and lava are the same substance in different places. When molten rock is underground, it is called magma. When it erupts onto the surface, it becomes lava. The difference is simply location. Magma originates deep in the Earth's mantle, or lower crust, where temperatures are high enough to melt rock. It is less dense than the surrounding solid rock, so it rises, seeking pathways through cracks and weaknesses in the crust. Sometimes it cools underground, forming intrusive igneous rocks like granite. Other times, it reaches the surface through volcanic vents and fissures. Once exposed to air or water, magma is renamed lava. It flows, cools, and solidifies into new land. In Hawaii, lava creates new coastline every day. In Iceland, it fills fissures and builds entire islands. The substance is the same, but the journey changes everything. Underground, magma is potential, hidden and waiting. Above ground, lava is transformation, creation and destruction made visible. Volcanoes are windows into the Earth's interior. When a volcano erupts, it does more than spew ash and lava. It offers a rare glimpse into the hidden layers of the planet. The rocks and gases that emerge from deep within carry information about conditions miles below the surface. Some volcanic rocks contain crystals that formed in the mantle. Others include fragments of the crust torn loose during ascent. Volcanic gases, especially sulfur and carbon dioxide, reveal the chemical composition of magma chambers. By studying eruptions, geologists can piece together what lies beneath our feet, far deeper than any drill could reach. Volcanoes are messengers from the deep earth. They speak in fire and stone, delivering samples from a realm we will never visit. Each eruption is a letter from the planet's interior, written in a language of heat and pressure, readable only to those willing to listen carefully. The Ring of Fire is a zone of intense volcanic and seismic activity. Circling the Pacific Ocean, is a vast arc of tectonic violence known as the Ring of Fire. It stretches from New Zealand, up through Japan, across to Alaska, and down the coasts of North and South America. This region is home to about 75% of the world's active volcanoes and experiences roughly 90% of the world's earthquakes. The Ring of Fire exists because the Pacific Plate is colliding with and sliding beneath several surrounding plates. Where plates meet, magma rises, volcanoes form, and earthquakes shake the ground. Cities like Tokyo, Los Angeles, and Manila sit within this zone, living daily with the knowledge that the earth beneath them is restless. Yet the same forces that bring danger also bring beauty. Volcanic soil is incredibly fertile, and the landscapes formed by eruptions are among the most dramatic on Earth. The Ring of Fire is a reminder that the planet is alive, that its crust is in constant motion, and that we build our lives on a surface that never truly rests. Earthquakes release energy that has been building for years. Deep underground, tectonic plates press against each other with immense force. Friction holds them in place, but stress continues to accumulate. Rock bends, compresses, and strains until finally it can hold no more. In an instant, the rock snaps back to its original shape, releasing all the stored energy in a violent shudder. This is earthquake. The point where the rock breaks is called the focus, and the point directly above it on the surface is the epicenter. Seismic waves radiate outward, shaking the ground and sometimes causing buildings to collapse, landslides to tumble, and tsunamis to form. The energy released in a major earthquake can be equivalent to thousands of atomic bombs. Yet it is only the sudden release of pressure that has been quietly building, sometimes for centuries. Earthquakes are not random acts of violence. They are the inevitable result of the planet's patient, grinding motions. The Earth moves slowly until it cannot. And then, all at once, it remembers how. Granite is one of the most common rocks on Earth's continents. If you've ever seen a polished countertop, a monument, or a hiking trail through the mountains, you've likely encountered granite. This igneous rock forms deep underground when magma cools slowly, allowing large crystals of minerals like quartz, feldspar, and mica to grow. Granite is strong, durable, and resistant to weathering, which is why it is so often used in construction. It is also extremely common. Much of the Earth's continental crust is made of granite, or rocks similar to it. Entire mountain ranges, like the Sierra Nevada in California, are composed largely of granite. Over millions of years, erosion exposes these deep rocks, bringing them to the surface where they form rugged peaks and boulder-strewn valleys. Granite is the backbone of continents, the foundation upon which landscapes are built. To stand on granite is to stand on stone that cooled in darkness, rose slowly through time, and now holds the light of the sky. Basalt is the most common rock on Earth's ocean floors. While granite dominates the continents, basalt rules the oceans. This dark, fine-grained igneous rock forms when lava erupts underwater or flows from volcanic vents and cools rapidly. Basalt makes up the vast majority of the ocean floor, formed continuously at mid-ocean ridges where tectonic plates pull apart. Magma rises to fill the gap, solidifies, and becomes new seafloor. This process, called seafloor spreading, has been creating basalt for hundreds of millions of years. Basalt is also found in volcanic islands like Hawaii and Iceland, where it builds entire archipelagos. It is denser and darker than granite, rich in iron and magnesium. When basalt weathers, It breaks down into fertile soil, which is why volcanic regions are often lush and green. Basalt is the hidden foundation of much of the planet. Beneath the waves, in places humans rarely see, it forms the floor of the world. Limestone forms from the remains of ancient sea creatures. Walk along a limestone cliff, and you are walking through an ancient ocean. Limestone is a sedimentary rock composed mostly of calcium carbonate, the same material that forms the shells and skeletons of marine organisms. Over millions of years, countless tiny creatures, corals, shellfish, and plankton lived, died, and sank to the ocean floor. Their remains accumulated in thick layers, compressing under the weight of sediment above. Water rich in dissolved minerals cemented the fragments together, creating solid rock. Sometimes, if you look closely, you can still see the shapes of shells and coral embedded in the stone. Limestone is a biological archive, a graveyard turned to rock. It forms the cliffs of Dover, the pyramids of Giza, and countless caves around the world. It is soft enough to carve, yet strong enough to endure, and it carries within it the memory of ancient seas, teeming with life, now pressed into silence and stone. Caves are carved by water, dissolving rock over thousands of years. Deep beneath the surface, where sunlight never reaches, water performs a slow and patient kind of sculpture. When rainwater seeps through soil, it absorbs carbon dioxide and becomes slightly acidic. This weak acid trickles through cracks in limestone or other soluble rocks, dissolving them bit by bit. Over thousands of years, narrow fissures widen into tunnels, and tunnels expand into vast chambers. Stalactites grow downward from the ceiling, where mineral-rich water drips and evaporates, leaving behind calcite deposits. Stalagmites rise from the floor, where those same drips land and build upward. Some caves contain underground rivers, lakes, and waterfalls. Others are completely dry, silent halls of stone, shaped entirely by water that has long since moved on. Caves are hidden galleries, carved in darkness and stillness. They remind us that even the hardest stone can be worn away, one drop at a time, by the patient persistence of water. Stalactites and stalagmites can take thousands of years to grow an inch. Inside a cave, time moves differently. Stalactites hang from the ceiling like frozen icicles, formed by water dripping slowly and leaving behind tiny amounts of dissolved minerals. Stalagmites rise from the floor where those drips land, building upward in mirror image. Both grow incredibly slowly, often taking 1,000 years or more to extend just a single inch. Some formations are tens of thousands of years old. They are records of climate, preserving chemical signatures from ancient atmospheres in their layers. When stalactites and stalagmites meet, they form a column, a pillar of stone connecting floor to ceiling. These formations are fragile despite their appearance. A single touch from a human hand can disrupt the delicate film of water that allows them to grow, effectively freezing them in time. Caves are living museums, and their formations are irreplaceable. They grow in darkness, unseen and unhurried, monuments to the power of patience. Geysers erupt when underground water is heated by magma. In certain volcanic regions, water seeps deep underground and encounters rock heated by magma. The water becomes superheated, far above its normal boiling point, but remains liquid under the pressure of the rock above. Eventually, the pressure becomes too great. Steam forces its way upward through narrow channels, and the water flashes into steam, erupting in a towering jet of boiling water and vapor. This is a geyser, a temporary fountain powered by the heat of the Earth's interior. Geysers are rare. They require a specific combination of heat, water, and plumbing-like rock structures. Yellowstone National Park contains more than half of the world's geysers, including Old Faithful, which erupts with remarkable regularity. Each eruption drains the underground reservoir, and the cycle begins again as water refills the chamber and is slowly reheated. Geysers are dramatic reminders that even in seemingly calm landscapes, the planet's inner fire is always close, always ready to break through the surface in bursts of steam and sound. Hot springs are windows into geothermal activity. Where magma lies close to the surface, it heats groundwater, which then rises and emerges as hot springs. The water can be warm, hot, or even scalding, rich in dissolved minerals that often give the pools vivid colors. In places like Iceland, Japan, and New Zealand, hot springs are common, fed by the heat of active volcanic systems. The minerals in the water, including sulfur, silica, and iron, can create stunning landscapes. Terraces of white travertine, pools ringed with red and orange bacteria, steaming blue lagoons. Some hot springs have been used for bathing for thousands of years, their warmth soothing, and their minerals thought to have healing properties. Others are too hot or acidic for any life, except extremophile bacteria, which thrive in conditions that would kill most organisms. Hot springs are places where the boundary between Earth's interior and its surface grows thin. They are portals, offering warmth from below, a reminder that the planet's heart still beats with heat. Obsidian is volcanic glass, formed when lava cools too quickly for crystals to form. When lava erupts and cools almost instantly, it solidifies into a smooth, glassy substance called obsidian. Unlike most igneous rocks, which have visible crystals formed as minerals slowly arrange themselves during cooling, obsidian cools so rapidly that atoms have no time to organize. The result is a rock that looks like black glass, smooth and reflective. Obsidian is extremely sharp when broken, sharper even than surgical steel. Ancient peoples prized it for making cutting tools, arrowheads, and knives. Even today, some surgeons use obsidian blades for delicate procedures because the edges are so fine. Obsidian forms near volcanoes, often in flows or domes where lava is exposed to air or water. It is fragile despite its hardness, easily shattered by a sharp blow. To hold obsidian is to hold frozen fire. Lava caught mid-transformation, a substance that never had time to become stone, and so became something else entirely. Glass, born of heat and speed. Pumice is the only rock that can float on water. After a volcanic eruption, you might find a strange rock bobbing in the sea. Pumice. This light-colored stone is filled with countless tiny air pockets, formed when gas-rich lava erupts explosively and cools while still frothy. The result is a rock so light and porous that it floats. Pumice has been found drifting across entire oceans, carrying marine organisms to distant shores. Despite its appearance, pumice is made of the same material as other volcanic rocks. It's the trapped air that makes it unique. In ancient Rome, pumice was used to smooth skin and soften fabric. Today, it is still used as an abrasive in cosmetics and even in lightweight concrete. Pumice is a paradox, a stone that defies gravity, a product of violence that floats gently on water. It is a reminder that even in geology, density is not destiny. Sometimes what seems heavy can be lifted by the spaces within. Sedimentary rocks form in layers, each representing a period of deposition. Look at a cliff of sedimentary rock, and you are looking at time made visible. Each layer, or stratum, represents a distinct period when sediment was deposited. Sand on a riverbed, mud at the bottom of a lake, shells accumulating on a seafloor. Over millions of years, these layers stack upon one another, compressing and hardening into rock. The principle of superposition tells us that, in undisturbed layers, the oldest rocks are at the bottom and the youngest at the top. By reading these layers, geologists can reconstruct ancient environments, track changes in climate, and even identify mass extinctions. Sometimes layers are tilted, folded, or broken by tectonic forces, adding complexity to the story. But the fundamental truth remains. Sedimentary rocks are time made solid, history written in stripes of sand, silt, and stone. Each layer is a page in Earth's autobiography. To read them is to travel backward through deep time. Coal formed from ancient forests buried and compressed over millions of years. The coal burned in power plants today is not a mineral. It is the compressed remains of plants that lived hundreds of millions of years ago. During the Carboniferous period, vast swampy forests covered much of the Earth. When trees and ferns died, they fell into stagnant water, where they were protected from decay. Over time, they were buried under layers of sediment. The weight and heat slowly transformed the plant material, first into peat, then into lignite, then into bituminous coal, and finally, under extreme pressure, into anthracite. Each stage represents a greater degree of compression and carbon concentration. Coal is fossilized sunlight, energy captured by ancient plants through photosynthesis and stored for eons. When we burn it, we release that energy, along with carbon that was locked away long before humans existed. Coal is a memory of green forests, now blackened by time and pressure, a reminder that even the oldest energy comes ultimately from the sun. Oil and natural gas formed from ancient marine organisms. Deep beneath the ocean floor, in sediments laid down millions of years ago, the remains of plankton, algae, and other microscopic organisms accumulated. Buried under layers of sediment, these organic materials were subjected to heat and pressure. Over millions of years, they transformed into hydrocarbons, oil, and natural gas. These fossil fuels are the compressed, chemically altered remnants of ancient life. They pooled in porous rock formations, trapped by impermeable layers above. Humans have drilled into these reservoirs for over a century, extracting the concentrated energy stored within. Like coal, oil, and gas are finite resources, the product of specific conditions that no longer exist on Earth. To use them is to burn the past, to release carbon that once drifted in Mesozoic seas. They are gifts from deep time, but also reminders that our energy comes at the cost of ancient ecosystems, transformed and stored in darkness. Metamorphic rocks are transformed by heat and pressure. When existing rocks are buried deep underground, they encounter conditions that change them fundamentally. Temperatures rise. Pressure increases. The minerals within the rock begin to recrystallize, rearranging themselves into new forms without melting. This process, called metamorphism, can transform sedimentary rocks, igneous rocks, or even other metamorphic rocks. Limestone becomes marble, its grains fusing into a smooth, crystalline stone, prized by sculptors. Shale becomes slate, compressed into thin, flat layers perfect for roofing. Granite subjected to extreme heat and pressure, can become gneiss, its minerals segregating into alternating light and dark bands. Metamorphic rocks bear the scars of their transformation. They are folded, banded, and contorted, evidence of the immense forces they endured. To hold a piece of metamorphic rock on is to hold proof that stone is not static. Under the right conditions, even the hardest rock will bend, change, and be reborn into something entirely new. Slate was once mud at the bottom of ancient seas. The slate used for roofing, chalkboards, and pool tables began as fine-grained mud deposited in quiet waters. Over time, this mud was buried and compressed into shale, a soft sedimentary rock. Then, deep underground, heat and pressure metamorphosed the shale into slate, aligning the clay minerals into parallel layers. This alignment allows slate to split cleanly into thin, flat sheets, a property called cleavage. Slate retains faint traces of its origin. Sometimes you can see ripples or fossils from the ancient seabed preserved in the stone. It is smooth, durable, and water-resistant, which is why it has been used by humans for centuries. Slate is a story of transformation, from soft mud to solid stone, from the bottom of a vanished ocean to the roofs of our homes. It is humble, yet elegant, proof that with enough time and pressure, even the softest material can become something strong. Marble is limestone that has been transformed by heat. The pure white marble of classical sculptures and grand buildings was once limestone, formed from the shells of ancient sea creatures. When limestone is buried deep in the Earth's crust and subjected to intense heat and pressure, its calcite crystals recrystallize into a denser, harder form, marble. The process erases most traces of fossils and sedimentary structures, leaving behind a smooth, crystalline rock. Pure marble is white, but impurities can add streaks of color. Iron creates reds and pinks, graphite produces gray or black, and serpentine adds green. Marble has been prized for millennia. Michelangelo carved David from Carrara marble. The Taj Mahal glows with white marble inlaid with colored stones. Despite its beauty, marble is softer than granite and more vulnerable to weathering, especially from acid rain. It is a stone of transformation, elegant and enduring, carrying within it the memory of ancient seas and the fire of metamorphosis. Minerals are the building blocks of rocks. Every rock is made of one or more minerals, naturally occurring solid substances with a specific chemical composition and crystal structure. Quartz, feldspar, mica, calcite, olivine. These are just a few of the thousands of minerals found on Earth. Each has unique properties. Quartz is hard and resistant to weathering. Mica splits into thin, flexible sheets. Calcite fizzes when touched by acid. Minerals form when atoms arrange themselves in repeating geometric patterns, creating crystals. Some crystals are microscopic. Others, like the giant gypsum crystals found in the Cave of Crystals in Mexico, can be over 30 feet long. The type and arrangement of minerals determine a rock's color, hardness, density, and how it weathers. Geologists identify rocks by examining their mineral content. To understand rocks, you must first understand minerals. They are the alphabet of geology, the fundamental units from which all stone is written. Crystals form when atoms arrange themselves in repeating patterns. A crystal is not just a pretty stone, it is a marvel of atomic order. When minerals form, their atoms bond in specific geometric arrangements that repeat in 3 dimensions. This internal structure gives crystals their characteristic shapes. The 6-sided columns of quartz, the cubic form of pyrite, the octahedrons of diamond. Crystals grow when conditions are right, usually in the presence of water or magma that allows atoms to move and find their places. The slower the growth, the larger and more perfect the crystals can become. Some crystals form in cavities called geodes, hollow rocks lined with sparkling points. Others grow in veins, cracks in rock filled with mineral-rich fluids. Crystals are proof that even at the atomic level, nature seeks order. They are geometry made visible, symmetry born from chaos, tiny universes of repeating structure hidden within the stone. Quartz is one of the most abundant minerals on Earth's surface. Quartz is everywhere. It forms the grains of sand on beaches, the sparkle in granite, the clear crystals prized by collectors. Chemically, quartz is silicon dioxide, one of the simplest and most stable compounds in Earth's crust. It is hard, resistant to weathering, and does not react easily with other substances. This durability means that when rocks break down, quartz grains persist, accumulating in riverbeds, deserts, and shorelines. Quartz comes in many varieties. Clear quartz is known as rock crystal. Purple quartz is amethyst. Pink quartz is rose quartz. Smoky quartz contains traces of radiation-damaged crystal structure. Quartz also has practical uses. It vibrates at a precise frequency when electricity is applied, making it essential in watches, computers, and radios. To hold quartz is to hold one of Earth's most fundamental substances, a mineral so common and so enduring that it forms the foundation of landscapes and the sand beneath your feet. Feldspar makes up more than half of Earth's crust. While quartz is common, feldspar is even more so. This group of minerals constitutes over 50% of the Earth's continental crust. Feldspar forms in igneous rocks like granite and basalt, and it also appears in many metamorphic rocks. There are two main types: potassium feldspar, which is often pink or white, and plagioclase feldspar, which ranges from white to grey. Feldspar is less resistant to weathering than quartz. When it breaks down, it forms clay minerals, which make up much of the world's soil. The weathering of feldspar also releases potassium, an essential nutrient for plants. So in a sense, feldspar is the parent of fertile soil. It is not as glamorous as gemstones, or as well known as quartz. But without feldspar, the world would be a very different place. It is the silent majority of the crust, the unnoticed foundation upon which continents rest. Mica splits into thin, flexible sheets. Mica is a mineral with a unique structure. Its atoms are arranged in sheets that are only weakly bonded to one another. This allows mica to split, or cleave, into thin, flexible layers that are almost paper thin, yet still solid. These sheets are translucent, heat-resistant, and excellent insulators. Before the widespread use of glass, mica was used in windows, stoves, and lanterns. It is still used today in electronics, cosmetics, and insulation. There are several types of mica. Muscovite is clear or silver. Biotite is black or dark brown. Both are common in igneous and metamorphic rocks. When granite weathers, mica flakes are released and often glitter in the sand and soil. To hold a sheet of mica is to hold something impossibly thin, yet surprisingly strong. A reminder that not all strength comes from hardness. Sometimes flexibility is its own kind of resilience. Gold is one of the few metals that occurs naturally in its pure form. Most metals are locked in ores, combined with oxygen, sulfur, or other elements. But gold is different. It is so unreactive that it often occurs as pure metal, embedded in quartz veins or scattered in riverbeds. Gold is dense, heavy, and does not tarnish or corrode. These properties, along with its rarity and beauty, have made it valuable for thousands of years. Gold forms deep underground, often in hydrothermal veins where hot, mineral-rich water deposits metals in cracks in the rock. Over time, erosion exposes these veins, and weathering breaks them apart. The gold, being heavy, settles in stream beds as flakes or nuggets, concentrated by the flow of water. Prospectors pan for gold by washing away lighter sediments, leaving the gold behind. To find gold is to find a fragment of the deep earth, carried upward by heat and time, resistant to every force that would dissolve it. It is a metal that endures, unchanging, a symbol of permanence in a world of transformation. Diamonds are the hardest natural substance on Earth. Formed over 1 billion years ago, deep in the mantle, diamonds are pure carbon. Each atom bonded to 4 others in an incredibly strong lattice. This structure makes diamonds the hardest known natural material. They can scratch anything, but nothing can scratch them except another diamond. Diamonds are brought to the surface by volcanic eruptions, carried upward in a matter of hours from depths of over 100 miles. Most diamonds are not gem quality. They are used industrially for cutting, drilling, and grinding. But the clear, flawless diamonds prized as gemstones are rare, valued not only for their beauty, but for their extraordinary journey. To hold a diamond is to hold something formed in unimaginable pressure, in darkness so deep no light has ever reached it, brought to the surface by violence, polished by human hands. It is the hardest thing nature makes, yet also one of the most brilliant when shaped to catch the light. Some minerals glow under ultraviolet light, shine a black light on certain minerals, and they seem to come alive, glowing with vivid colors. This property, called fluorescence, occurs when ultraviolet light excites electrons in the mineral, causing them to emit visible light. Fluorite often glows blue or purple. Calcite can glow red, orange, or even green. Willemite, a zinc silicate, glows bright green. The effect is startling and beautiful, transforming dull stones into radiant gems. Not all minerals fluoresce, and even within a single mineral species, only certain specimens do, depending on the trace elements they contain. Fluorescence has practical uses too. It helps geologists identify minerals in the field and can reveal hidden ore deposits. But beyond its utility, fluorescence is a reminder that the world is full of hidden beauty, visible only when we look in the right way, with the right light. Erosion shapes the landscape over millions of years. Wind, water, ice, and gravity are the great sculptors of the Earth's surface. Erosion is the process by which rock and soil are worn away and transported from one place to another. Rivers carve valleys. Glaciers gouge out fjords. Wind shapes sand dunes. Rain dissolves limestone, creating caves and sinkholes. The Grand Canyon, the cliffs of Yosemite, the stone arches of Utah, all are masterpieces of erosion, shaped patiently over millions of years. Erosion works slowly, grain by grain, but its effects are profound. Mountains are worn down to plains. Coastlines retreat. Entire landscapes are reshaped. What erosion removes, it deposits elsewhere. River deltas, alluvial plains, sand dunes, erosion and deposition are two sides of the same process, a constant exchange of material driven by the energy of wind, water, and ice. The Earth's surface is never still. It is always being dismantled and rebuilt, sculpted by forces that never rest. Glaciers are rivers of ice that carve deep valleys. A glacier is not just frozen water. It is a river of ice that flows, slowly but powerfully, under its own weight. Glaciers form in places where more snow falls in winter than melts in summer. Over years, the snow compacts into ice, and the mass begins to move downhill. As it flows, the glacier grinds against the bedrock, plucking rocks from the valley floor and walls, carrying them along like tools. This process, called glacial erosion, carves deep U-shaped valleys, creates cirques, and polishes bedrock into smooth surfaces. When glaciers retreat, they leave behind moraines, piles of rock and sediment, and sometimes large boulders called erratics, deposited far from their source. The landscapes of Yosemite, the fjords of Norway, the Great Lakes, all were shaped by glaciers during the last ice age. Glaciers are among the most powerful agents of erosion. They reshape entire regions, carving the bones of the landscape into new forms, slow and patient and unstoppable. The last ice age ended about 12,000 years ago. For over 2 million years, Earth cycled through periods of intense cold and relative warmth. During the last glacial maximum, around 20,000 years ago, ice sheets covered much of North America, Europe, and Asia. Sea levels were lower because so much water was locked in ice. The climate was drastically different. Then the ice began to retreat. By about 12,000 years ago, the glaciers had melted back significantly. Sea levels rose, and the climate warmed. This transition marked the end of the Pleistocene and the beginning of the Holocene, the epoch in which we still live. The melting ice left behind the landscapes we see today. The Great Lakes, the fjords of Scandinavia, the rolling hills of the American Midwest. Humans who had lived through the Ice Age now spread across newly habitable land. The world we know is a product of that warming, a landscape still shaped by the ghosts of vanished glaciers. Sand is mostly tiny fragments of quartz and feldspar. Walk on a beach and you are walking on the remains of mountains. Sand is not a single substance, but a size category, particles between 0.06 and 2 millimeters. Most sand is composed of quartz and feldspar, minerals that resist weathering and are abundant in continental rocks. When rocks erode, softer minerals break down into clay, but quartz and feldspar grains persist. Rivers carry these grains to the sea, where waves sort and deposit them on beaches. Some sand is made of other materials. Volcanic beaches have black sand from basalt. Tropical beaches have white sand from coral and shells. The color and composition of sand tell the story of the rocks from which it came. Each grain is a fragment of a larger story, a piece of a distant mountain, smoothed and rounded by its journey, finally coming to rest on the shore. Deserts are shaped by wind and rare rainstorms. Deserts are not lifeless wastelands, but landscapes of surprising dynamism. Wind is the primary sculptor here, lifting fine particles and leaving behind coarser sand and gravel. Sand dunes form when wind deposits sand in patterns dictated by wind direction and strength. Some dunes are crescent-shaped, others form long ridges. Still others pile into star-shaped mounds. When rain does fall in a desert, it falls hard and fast. Because the ground is dry and often hard-packed, water does not soak in. It runs off rapidly, carving deep channels called arroyos or wadis. Flash floods are common, powerful enough to move boulders and reshape valleys in hours. Desert landscapes are stark and dramatic. Mesas, buttes, slot canyons. They are shaped by extremes, by the abrasive force of wind and the sudden violence of water. In the desert, Erosion and deposition happen quickly when they happen at all, creating a landscape that is both ancient and constantly changing. Canyons form when rivers cut through rock over millions of years. A canyon is a testament to the power of persistence. Rivers, though they seem gentle, are among the most effective agents of erosion. As water flows downhill, it carries sediment that acts like sandpaper, grinding away at the riverbed. Over millions of years, a river can cut through thousands of feet of rock, carving a deep canyon. The process is fastest in areas where the land is uplifting, forcing the river to cut downward to maintain its course. The Grand Canyon, carved by the Colorado River, is the most famous example. The river has been cutting through rock for about 6 million years, exposing layers that are up to 2 billion years old. Canyons are also shaped by weathering and mass wasting, rockfalls, landslides, and the gradual crumbling of cliff faces. They are dynamic features, constantly evolving. A canyon is time made visible, a wound in the Earth's surface that reveals the strata of history, layer by layer. Rivers carry more than water. They transport sediment. Every river is a conveyor belt, moving not just water, but rock, sand, and silt from higher elevations to lower ones. The amount of sediment a river carries depends on its speed and volume. Fast-flowing mountain streams can move boulders. Slower rivers carry sand and mud. When a river slows down, such as when it enters a lake or ocean, it drops its sediment. This process, called deposition, builds deltas, alluvial plains and floodplains. The Mississippi Delta, for example, is built entirely from sediment carried down from the interior of North America. Over thousands of years, rivers redistribute the landscape, wearing down mountains and filling in basins. The sediment they carry eventually becomes sedimentary rock, preserving a record of the river's ancient work. Rivers are the arteries of the earth, moving material from place to place, sculpting valleys, and building new land at their mouths. Floodplains are among the most fertile lands on Earth. When a river overflows its banks, it spreads water and sediment across the surrounding land. This area, called a floodplain, is enriched by the nutrients and minerals in the sediment. Ancient civilizations, from Egypt to Mesopotamia to the Indus Valley, flourished on floodplains, relying on annual floods to replenish the soil. Flooding is a natural and essential process, though modern societies often try to prevent it with levees and dams. Floodplains also act as natural buffers, absorbing excess water and reducing the impact of floods downstream. When we build on floodplains and prevent rivers from spreading, we disrupt this balance. The sediment that should nourish fields instead piles up behind dams or gets carried out to sea. Floodplains remind us that rivers are dynamic systems, and that the richest land is often found where water and stone meet in cycles of renewal. Soil is a mixture of weathered rock, organic matter, air, and water. Soil is easy to overlook, but it is one of the most complex and essential substances on Earth. It forms slowly as rock weathers and breaks down, as plants grow and die, as organisms burrow and mix the material. A single handful of soil contains billions of bacteria, fungi, and other microorganisms. It also contains minerals from the parent rock, organic matter called humus, water, and air. Soil takes thousands of years to form, but can be lost in a single generation through erosion or poor management. Different types of rock produce different soils. Granite weathers into sandy, acidic soil. Limestone produces rich, alkaline soil. Volcanic rock weathers into extremely fertile soil. Soil is where geology and biology meet. It is the interface between the living and the non-living, the foundation of agriculture and ecosystems. Without soil, there would be no plants, no forests, no food. It is quite literally the ground beneath our feet. Weathering breaks down rocks without moving them. Weathering is the slow disintegration of rock caused by exposure to the atmosphere, water, and biological activity. It happens in place, unlike erosion, which transports material. Physical weathering occurs when rocks crack and break apart due to temperature changes, frost, or plant roots growing in cracks. Chemical weathering occurs when minerals react with water, oxygen, or acids, dissolving or transforming into new minerals. For example, feldspar weathers into clay. Iron-rich minerals rust. Limestone dissolves in acidic rainwater. Biological weathering happens when organisms, from lichens to tree roots, break down rock. Weathering is the first step in the rock cycle, the process that turns solid stone into sediment. It is slow and subtle, but over time, it can reduce mountains to plains. Weathering reminds us that even stone is temporary. Given enough time, the hardest rock will crumble into dust. Icebergs are freshwater ice floating in saltwater oceans. When glaciers reach the sea, chunks break off and float away, forming icebergs. These massive pieces of ice are freshwater, formed from compacted snow that fell on land, sometimes thousands of years ago. Icebergs can be enormous. The largest ever recorded was over 200 miles long. Most of an iceberg's mass is underwater, hidden beneath the surface. Only about 10% is visible, which is why they are so dangerous to ships. As icebergs drift into warmer waters, they melt, releasing ancient fresh water into the salty ocean. This process can affect ocean currents and even local ecosystems. Icebergs are reminders of the vast ice sheets that still cover Greenland and Antarctica. They are pieces of the past, fragments of glaciers that began forming long before human civilization, now adrift in a warming world. Sinkholes form when underground rock dissolves and collapses. In regions with limestone bedrock, water seeping underground can slowly dissolve the rock, creating cavities and caves. Sometimes, the roof of one of these cavities becomes so thin that it collapses, forming a sinkhole. Sinkholes can appear suddenly, swallowing roads, buildings, and entire ponds. They can also form gradually, creating depressions that slowly deepen over time. Some sinkholes fill with water, forming lakes or ponds. Others remain dry. In places like Florida and the Yucatan Peninsula, sinkholes are common and can be quite large. The ancient Maya used water-filled sinkholes, called cenotes, as sources of fresh water. Sinkholes are dramatic evidence that the ground beneath our feet is not always solid. Water, patient and persistent, can dissolve even the hardest limestone, creating hidden voids that may one day collapse into the light. Earth's continents are slowly drifting apart and coming together. The continents are not fixed. They drift across the surface of the planet, driven by the slow churning of the Earth mantle below. Right now, North America and Europe are moving apart at about the rate your fingernails grow as the Atlantic Ocean widens. Meanwhile, Africa is moving northward toward Europe, slowly closing the Mediterranean Sea. In about 50 million years, the two continents may collide, forming a new mountain range. Australia is drifting north toward Asia. The Pacific Ocean is shrinking as plates converge. These movements are part of the Wilson cycle, the process by which supercontinents form, break apart, and reform over hundreds of millions of years. In the distant future, some geologists predict that the continents will merge into a new supercontinent, perhaps called Pangaea Proxima. The map of Earth is always changing, slowly and inexorably, driven by forces we are only beginning to understand. The Mohorovičić discontinuity marks the boundary between crust and mantle. Deep beneath the surface, there is a boundary that marks a fundamental change in the Earth's structure. This boundary, called the Mohorovičić discontinuity, or MOHO for short, separates the crust from the mantle. Above the MOHO, rocks are relatively light and brittle. Below it, the mantle is denser and behaves differently under pressure. The MOHO is not at a constant depth. Under continents, it is about 30 to 50 kilometers down. Under oceans, it is much shallower, only about 5 to 10 kilometers below the seafloor. The MOHO was discovered in 1909 by Croatian seismologist Andrija Mohorovičić, who noticed that seismic waves change speed at a certain depth. This change indicated a difference in material. The MOHO is a reminder that the Earth is layered, not homogeneous, and that beneath the thin skin we inhabit lies a different world entirely. Earth's mantle is solid, but flows like a very thick liquid. It is easy to imagine the mantle as molten rock, a sea of liquid magma, but the mantle is actually solid, made of hot, dense rock. However, over long periods of time, it behaves like a very thick fluid. Under immense heat and pressure, solid rock can flow, a process called plastic deformation. This slow movement, called mantle convection, drives plate tectonics. Hot rock rises from deep in the mantle, cools as it nears the surface, and then sinks back down. These convection currents drag the tectonic plates above them, causing continents to drift, oceans to open and close, and mountains to rise. The mantle flows at a rate of a few centimeters per year, imperceptibly slow, but immensely powerful. It is a reminder that solidity is relative. Given enough time and pressure, even stone can flow. The Earth's core is as hot as the surface of the sun. At the center of the Earth, nearly 4,000 miles below the surface, lies the core. It consists of two parts, a liquid outer core and a solid inner core, both made primarily of iron and nickel. Temperatures in the core reach about 5,400 degrees Celsius, roughly the same as the surface of the sun. The intense heat comes from the radioactive decay of elements and the residual heat from Earth's formation over 5 billion years ago. The liquid outer core is in constant motion, and this movement generates Earth's magnetic field through a process called the geodynamo. The solid inner core, despite being even hotter, remains solid because of the immense pressure at the center of the planet. The core is unreachable, unknowable, except through indirect measurement. But it is the heart of the planet, the source of the magnetic field that shields us from solar radiation, the furnace that keeps the mantle flowing. Earth's magnetic field protects us from solar radiation. High above the atmosphere, an invisible shield surrounds the Earth. This is the magnetosphere, generated by the movement of molten iron in the outer core. The magnetic field deflects most of the charged particles streaming from the sun, known as the solar wind. Without this protection, the solar wind would strip away the atmosphere, as it has done on Mars. The magnetic field also creates the auroras, the northern and southern lights, when solar particles interact with gases in the upper atmosphere. The field is not static. It shifts and fluctuates, and occasionally it reverses. The north and south magnetic poles swap places. This has happened hundreds of times in Earth's history, recorded in the magnetic signatures of rocks formed at mid-ocean ridges. We live under the protection of a magnetic umbrella, generated by a churning sea of metal thousands of miles beneath our feet. It is one of the many invisible forces that make life on Earth possible. Fossils tell us about Earth's climate in the past. When geologists find fossils of tropical plants in Antarctica or coral reefs in the Arctic, they know that the climate was once very different. Fossils are not just records of ancient life. They are records of ancient environments. The types of organisms, the sediments they are found in, and the chemistry of the fossils themselves all provide clues about temperature, humidity, sea level, and atmospheric composition. Ice cores drilled from polar ice sheets contain bubbles of ancient air, preserving samples of the atmosphere from hundreds of thousands of years ago. Tree rings record annual growth and can reveal droughts, floods, and temperature changes. By studying these natural archives, scientists can reconstruct Earth's climate history, understanding how it has changed in the past, and using that knowledge to predict future changes. The past is written in stone, ice, and bone, waiting to be read by those who know how to look. Mass extinctions are recorded in the rock layers. 5 times in Earth's history, life has come close to being wiped out entirely. These events, called mass extinctions, are recorded in the fossil record as sudden disappearances of species. The most famous is the extinction at the end of the Cretaceous period, 66 million years ago, which killed the non-avian dinosaurs. It is marked by a thin layer of clay, rich in iridium, a metal rare on Earth, but common in asteroids. This layer is found worldwide, evidence of a massive impact. Other mass extinctions have different causes: volcanic eruptions, climate change, ocean acidification. The Permian extinction, 252 million years ago, was the worst of all, killing over 90% of species. After each extinction, life recovered, evolving new forms to fill empty niches. Mass extinctions are reminders of the planet's violence and resilience. The rock layers do not lie. They show us that life is fragile, but also that it endures. Some rocks are magnetized in the direction of ancient magnetic fields. When lava cools, iron-rich minerals within it align with Earth's magnetic field and lock into place. This process, called remanent magnetization, creates a permanent record of the field's direction at the time the rock formed. By studying these magnetic signatures, geologists discovered that the magnetic field has reversed many times throughout history. Rocks formed during normal polarity point north. Rocks formed during reversed polarity point south. The seafloor, formed continuously at mid-ocean ridges, contains a striped pattern of magnetic reversals that mirrors on either side of the ridge. This was one of the key pieces of evidence that proved seafloor spreading and plate tectonics. Rocks remember the magnetic field of the past, preserving it like a compass frozen in time. This paleomagnetic record allows scientists to reconstruct the positions of continents, the opening and closing of oceans, and the history of Earth's magnetic field over hundreds of millions of years. Some minerals contain radioactive elements that decay over time. Certain elements, like uranium, thorium, and potassium, are radioactive. Their atoms are unstable and decay at a predictable rate. transforming into other elements and releasing energy. This process, called radioactive decay, happens at a constant rate that is not affected by temperature, pressure, or chemical reactions. By measuring the ratio of parent isotopes to daughter isotopes in a rock, geologists can determine how much time has passed since the rock formed. This technique, called radiometric dating, has allowed scientists to determine the age of the Earth, approximately 4.54 billion years. Different isotopes decay at different rates, making some useful for dating very old rocks, and others for dating younger materials. Radioactive decay is a natural clock, ticking steadily inside the minerals of every rock. It has unlocked the timeline of Earth's history, revealing the age of mountains, fossils, and the planet itself. Earth is about 4.54 billion years old. For most of human history, the age of the Earth was a mystery. Religious texts suggested thousands of years. Early geologists, observing erosion and sedimentation, guessed millions. It was not until the discovery of radioactivity that scientists could measure Earth's age with precision. By dating meteorites, which formed at the same time as the solar system, and ancient rocks from Earth's crust, scientists determined that the planet is about 4.54 billion years old. This number is almost incomprehensible. If you compressed Earth's history into a single year, humans would appear only in the last few minutes before midnight on December 31st. The age of the Earth is a reminder of the vastness of geological time, the deep history written in stone, and the fleeting nature of our own existence in comparison. Time sixes. The oldest known mineral on Earth is a zircon crystal, 4.4 billion years old. In the Jack Hills of Western Australia, geologists have found tiny zircon crystals that formed over 4.4 billion years ago, just 100 million years after Earth itself formed. Zircons are incredibly durable. They resist weathering, heat, and pressure, preserving their structure and composition even as the rocks around them are destroyed and reformed. By analyzing the isotopes within these ancient zircons, scientists can learn about the conditions on early Earth. The crystals suggest that liquid water, and possibly even continents, existed far earlier than once thought. These tiny grains are time capsules, older than any rock, older than the oldest fossils, older than the moon. To hold one is to hold a fragment of the infant Earth, a survivor from a time when the planet was still being bombarded by asteroids, and the surface was cooling from molten chaos. Water has been shaping Earth's surface for billions of years. Water is the most powerful force in geology. It weathers rock, transports sediment, carves valleys, and deposits new land. It dissolves minerals, creating caves, and precipitates them, forming stalactites. Water drives the rock cycle, facilitating chemical reactions that transform minerals. It fills the oceans, which cover over 70% of the planet's surface. Water has been present on Earth for most of its history, and evidence suggests it existed in some form even in the earliest days, shaping the first continents and oceans. Water is also essential for plate tectonics. It lowers the melting point of rock in the mantle, allowing magma to form and volcanoes to erupt. Without water, Earth would be a very different planet, dry and geologically dead, like Mars. Water connects every part of the Earth system. It cycles through the atmosphere, oceans, crust, and mantle, shaping the surface and sustaining life. Earth's atmosphere was created by volcanic outgassing. The early Earth had no atmosphere, or at least not one anything like today's. The primordial gases were likely blown away by the solar wind. The atmosphere we have now was created by volcanic eruptions. For billions of years, volcanoes released gases from the planet's interior: water vapor, carbon dioxide, nitrogen, and small amounts of other gases. The water vapor condensed into oceans. Photosynthetic organisms, first cyanobacteria and later plants, began producing oxygen, gradually transforming the atmosphere into one that could support complex life. The atmosphere is not a fixed feature. It has evolved over time, shaped by geology and biology. The air we breathe is the product of volcanic fire, ancient oceans, and the quiet work of microbes over eons. It is a gift from the deep earth, a blanket of gas that makes life possible. Tectonic plates move at about the same rate that fingernails grow. The movement of continents is imperceptibly slow. Most tectonic plates move at a rate of a few centimeters per year, about the same speed that your fingernails grow. Yet this slow motion is powerful enough to build mountains, open oceans, and reshape the globe. Over millions of years, these tiny movements accumulate. A few centimeters per year becomes hundreds of kilometers over 10 million years, thousands of kilometers over 100 million years. The Atlantic Ocean is about 3,000 miles wide, but it was once closed. It has been opening at a rate of a few centimeters per year for about 180 million years. Plate tectonics is geology's slow heartbeat, the rhythm by which the planet breathes and changes. We cannot see it happening, but the evidence is everywhere, in the fit of continents, in the patterns of earthquakes, in the chains of volcanoes that circle the Pacific. The Himalayas were once the floor of the Tethys Sea, before the Himalayas rose. A vast ocean called the Tethys Sea stretched between the ancient continents of Gondwana and Laurasia. The floor of this ocean was covered with sediments, sand, mud, and the remains of countless marine organisms. Around 50 million years ago, the Indian subcontinent, which had broken away from Gondwana, collided with Asia. The ocean floor was crumpled and thrust upward, and the sediments were folded into the highest mountains on Earth. This is why you can find marine fossils, ammonites, and sea lilies on the slopes of Mount Everest. The Himalayas are the ocean turned inside out, the seabed lifted miles into the sky. They are proof that the Earth's surface is not fixed, that oceans can close, and that the bottom of the world can become the top. The Tethys Sea is gone, but its memory lives on in the limestone peaks that scrape the heavens. Earth's geology influences where we build cities and how we live. Geology is not just an academic subject. It shapes human civilization. Cities are built on stable ground, often near rivers for water and transportation. Ports are built in natural harbors, shaped by tectonic activity or glacial erosion. Agriculture depends on fertile soil, which depends on the underlying bedrock. Earthquakes, volcanoes, landslides, and floods are all geological hazards that influence where and how we build. We mine minerals for metals, drill for oil and gas, and quarry stone for construction. Geology provides the resources that power modern life. Understanding geology helps us predict natural disasters, find clean water, and manage resources sustainably. It reminds us that we are not separate from the Earth. We live on it, shaped by its processes, dependent on its materials. To ignore geology is to ignore the foundation upon which everything else rests. Every rock has a story. Hold a stone in your hand, and you are holding a piece of Earth's history. That rock may have formed in a volcanic eruption, cooled from molten lava, or been deposited grain by grain at the bottom of an ancient sea. It may have been buried deep in the crust, compressed and heated until its minerals transformed. It may have been lifted by tectonic forces, exposed by erosion, carried by rivers, and finally come to rest where you found it. Every crack, every mineral, every texture tells part of the story. Geologists read rocks like historians read documents. They see time in layers, motion in folds, heat in crystals. To study geology is to learn the language of stone, to hear the whispers of deep time. Every rock is a traveler, a survivor, a fragment of a larger narrative that stretches back billions of years. The Earth is still writing this story, one grain at a time. The San Andreas Fault is slowly moving Los Angeles towards San Francisco. Along the coast of California runs one of the most famous geological features in North America, the San Andreas Fault. This is not a single crack, but a complex zone where the Pacific Plate slides past the North American Plate. The motion is horizontal, called strike slip, and it happens at a rate of about 2 inches per year. Over millions of years, this small movement adds up. Los Angeles, which sits on the Pacific Plate, is slowly moving northwest towards San Francisco, which sits on the North American Plate. In about 15 million years, if the motion continues, they may be side by side. The fault is also responsible for earthquakes. When the plates stick and then suddenly slip, the ground shakes. The 1906 San Francisco earthquake, one of the most destructive in American history, was caused by movement along the San Andreas Fault. The fault is a scar on the landscape, a visible reminder that the ground beneath California is in motion, quietly, constantly, carrying cities toward each other at the pace of a growing fingernail. Some gemstones form in metamorphic rocks under intense pressure, deep underground, where heat and pressure transform rock. Some of the world's most beautiful gemstones are born. Rubies and sapphires form in metamorphic rocks like marble and schist, when aluminum oxide crystallizes under high pressure. Emeralds form when beryllium, aluminum, and silicate combine in metamorphic environments enriched with chromium or vanadium. These gemstones are rare because the conditions required for their formation are rare. They need just the right combination of elements, temperature, and pressure, sustained over millions of years. When tectonic forces later uplift these rocks and erosion exposes them, gemstones emerge. They are fragments of the deep crust brought to light, polished by nature, and later by human hands. To wear a ruby or emerald is to carry a piece of metamorphism, beauty born from pressure, color crystallized from chaos. Amber is fossilized tree resin, millions of years old. Long ago, trees oozed sticky resin to seal wounds and protect themselves from insects and disease. Sometimes small creatures, insects, spiders, even tiny frogs became trapped in the resin. Over millions of years, as the resin was buried and subjected to heat and pressure, it hardened into amber, a golden, translucent gemstone. The creatures inside were preserved in exquisite detail, their bodies protected from decay. Amber offers a unique window into ancient ecosystems. Scientists have found feathers, leaves, flowers, and even droplets of water trapped in amber, frozen in time. The oldest amber is over 300 million years old. It is not a mineral, but it is geological. Fossilized resin, organic in origin, but transformed by time and geology into something beautiful and enduring. Amber is a moment captured, life suspended in golden stone. Petrified wood is ancient wood turned to stone. In certain conditions, when wood is buried rapidly in sediment and deprived of oxygen, it does not decay. Instead, mineral-rich water seeps into the wood cells. Over time, the minerals, often silica, replace the organic material, molecule by molecule, preserving the structure of the wood in stone. The result is petrified wood, rock that looks exactly like wood, complete with bark, growth rings, and even the texture of the original tree. Some petrified wood is over 200 million years old, from forests that existed long before flowering plants or dinosaurs. Petrified wood is stunning. The minerals often create vibrant colors: reds from iron, yellows from uranium, greens from copper. It is a fossil, but unlike most fossils, it is not just an impression or a replica. It is the tree itself, transformed from carbon into quartz, from life into stone. Geothermal energy comes from Earth's internal heat. Beneath the surface, the Earth is hot. This heat, left over from the planet's formation and continuously generated by radioactive decay, is a vast and largely untapped source of energy. In volcanic regions where magma lies close to the surface, this heat can be harnessed. Wells are drilled deep into the crust, and water is pumped down. The hot rocks heat the water, turning it into steam, which is then used to drive turbines and generate electricity. This is geothermal energy. Iceland, sitting atop the mid-Atlantic ridge, derives much of its power from geothermal sources. Other countries like Kenya, the Philippines, and New Zealand also use geothermal energy. It is a clean, renewable source of power, drawn from the planet's own internal furnace. The heat that drives plate tectonics and volcanoes can also light homes and warm buildings. The Earth, in its depths, holds fire enough to power civilizations. Earth's interior is explored using seismic waves from earthquakes. We cannot drill to the center of the Earth. The deepest hole ever dug, the Kola super deep borehole in Russia, reached only about 7.5 miles, a fraction of the distance to the core. So how do we know what lies beneath? The answer is seismic waves. When an earthquake occurs, it sends waves of energy radiating through the Earth. Different types of waves travel at different speeds and through different materials. By placing seismometers around the world and recording how long it takes waves to arrive and how they change as they pass through different layers, scientists can map the Earth's interior. They have discovered the crust, mantle, outer core, and inner core this way. Seismic waves reveal that the outer core is liquid because certain waves cannot pass through it. They show that the inner core is solid, despite being hotter, because of the immense pressure. Earthquakes, though destructive, are also informative. They allow us to see into the hidden heart of the planet. The seafloor is younger than the continents. While the oldest rocks on the continents are over 4 billion years old, the oldest seafloor is only about 200 million years old. This is because seafloor is constantly being created and destroyed. At mid-ocean ridges, new seafloor forms as magma rises and solidifies. As the seafloor spreads away from the ridge, it eventually reaches a subduction zone, where it is pushed back down into the mantle and recycled. This process, called seafloor spreading and subduction, means the ocean floor is young compared to the continents. Continents, being less dense, are not subducted. They remain at the surface, accumulating history layer upon layer. The seafloor, by contrast, is transient, constantly renewed, constantly consumed. It is a surface in motion, the youngest part of Earth's crust, a reminder that the planet is not finished, that creation and destruction happen continuously. Mid-ocean ridges are underwater mountain ranges where new crust is born. Beneath the oceans, hidden from view, are some of the longest mountain ranges on Earth. Mid-ocean ridges stretch for over 40,000 miles, winding through every ocean basin. At these ridges, tectonic plates are pulling apart. As they separate, magma from the mantle rises to fill the gap, cooling and solidifying into new oceanic crust. This process is called seafloor spreading. The ridges are not smooth. They are jagged, volcanic, and geologically active, with hydrothermal vents spewing superheated water rich in minerals. These vents support unique ecosystems, communities of organisms that thrive without sunlight, relying instead on chemicals from the Earth's interior. Mid-ocean ridges are the birthplaces of ocean basins, the seams where the planet knits new crust, quietly, continuously, in the cold darkness of the deep sea. Hydrothermal vents on the ocean floor support unique ecosystems. In the lightless depths of the ocean, where no photosynthesis is possible, life has found another way. Hydrothermal vents, also called black smokers, are fissures on the seafloor where superheated water, rich in minerals and chemicals, spews into the cold ocean. Bacteria around these vents use chemosynthesis, deriving energy from chemicals like hydrogen sulfide instead of sunlight. These bacteria form the base of a unique food web. Around the vents, entire ecosystems thrive. Giant tube worms, eyeless shrimp, white crabs, and strange fish. These creatures live in one of the most extreme environments on Earth, in darkness, under crushing pressure, near water hot enough to melt lead. The discovery of hydrothermal vent ecosystems in the 1970s changed our understanding of life. It showed that life can exist without sunlight, that it can adapt to conditions once thought impossible. These vents are geology and biology intertwined, proof that wherever there is energy, life finds a way. Some rocks contain bubbles of ancient atmosphere. Volcanic rocks that cooled quickly sometimes trap bubbles of gas, preserving samples of the ancient atmosphere. Amber can contain bubbles of air from forests millions of years ago. Ice cores drilled from glaciers contain tiny pockets of air that are hundreds of thousands of years old. By analyzing the composition of these trapped gases, scientists can learn about the Earth's past atmosphere, how much carbon dioxide, methane, and oxygen it contained. This data helps us understand past climates, how they changed, and what caused those changes. The bubbles are time capsules, messages from the past written in molecules. They tell us that the atmosphere has not always been as it is now. It has been richer in carbon dioxide, warmer. It has been colder, with less greenhouse gas. These ancient breaths help us predict the future by understanding the past. Subduction. Zones are where tectonic plates dive back into the mantle. At subduction zones, oceanic crust, dense and cold, is pushed beneath another plate and descends into the mantle. As it sinks, it heats up, releasing water and triggering partial melting of the surrounding mantle. This molten rock rises, forming chains of volcanoes on the overriding plate. The Pacific Ring of Fire is largely made up of subduction zones. Subduction is one of the ways the Earth recycles its crust. Old seafloor, which formed at mid-ocean ridges, eventually returns to the mantle, completing the cycle. Subduction zones are also the sites of the world's largest earthquakes. As plates grind past each other, friction builds until the rock finally snaps, releasing enormous energy. The 2011 Tohoku earthquake in Japan, the 2004 Indian Ocean earthquake, and the 1960 Chilean earthquake, the largest ever recorded, all occurred at subduction zones. These are the planet's pressure valves, where the stress of tectonic motion is released in shudders and fire. The Great Rift Valley in Africa is a continent tearing apart. In East Africa, the continent is splitting. The Great Rift Valley is a massive geological feature where the African plate is being pulled apart by tectonic forces. The rift stretches for thousands of miles, from the Red Sea in the north to Mozambique in the south. As the land pulls apart, the crust thins and sinks, forming a long valley. Volcanoes erupt along the rift, and lakes fill the lowest areas. Over millions of years, if the rifting continues, the eastern part of Africa will break away entirely, and a new ocean will form between the separated landmasses. The Red Sea and the Gulf of Aden are examples of this process further along. They were once rift valleys and are now young, narrow oceans. The Great Rift Valley is a window into the future, a place where we can watch a continent beginning to split, slowly, inexorably, driven by the restless motion of the mantle below. Igneous intrusions can form massive underground rock formations. Not all magma erupts. Much of it cools slowly underground, forming large bodies of rock called igneous intrusions or plutons. The largest of these, called batholiths, can be hundreds of miles across. As magma cools slowly deep in the crust, large crystals have time to form, creating coarse-grained rocks like granite. Over millions of years, erosion removes the overlying rock, exposing these intrusions at the surface. The Sierra Nevada mountains in California are largely made of granite from a massive batholith. Stone Mountain in Georgia, Half Dome in Yosemite, and many other famous landmarks are exposed plutons. These formations are monuments to the slow work of geology, rock that cooled in darkness and is now revealed in light, shaped by erosion into domes, cliffs, and peaks that define the landscape. Some minerals are so rare, they're found in only one place on Earth. Most minerals are widespread, found in many locations around the globe. But some are incredibly rare, formed under such specific conditions that they exist in only one or a few places. Painite, once considered the rarest mineral on Earth, was found only in Myanmar for decades. Benitoite, California's state gem, is found in gem quality only in San Benito County. Red beryl, a rare form of beryl, is found primarily in Utah. These minerals form when unusual combinations of elements come together under just the right temperature and pressure. Their rarity makes them valuable to collectors and scientists alike. They are geological anomalies, reminders that the conditions under which rocks form are endlessly variable, and that even after centuries of study, the Earth can still surprise us with something new, something unique, something found nowhere else. Meteorite impacts have shaped Earth's geology. Throughout its history, Earth has been bombarded by meteorites. Most burn up in the atmosphere, but some have been large enough to reach the surface and leave lasting marks. The Chicxulub crater in Mexico, buried under sediment, is the scar left by the asteroid that ended the age of dinosaurs. The impact released energy equivalent to billions of atomic bombs, triggering wildfires, tsunamis, and a cloud of debris that blocked the sun for years. Meteorite impacts have also brought materials to Earth that are rare in the crust, like iridium and platinum. They have excavated deep layers of rock, exposing ancient formations. Some scientists even believe that meteorites delivered water and organic molecules to the early Earth, ingredients essential for life. Impacts are rare now, but they have profoundly influenced the planet's surface, climate, and even the evolution of life. They are violent, sudden events in a world otherwise shaped by slow, patient processes. Earth has been hit by meteorites carrying water and organic compounds. In the early days of the solar system, Earth was a hot, molten world, and any water on its surface would have boiled away. Yet today, oceans cover most of the planet. Where did the water come from? One theory is that it was delivered by comets and asteroids that bombarded the Earth during a period called the Late Heavy Bombardment, about 4 billion years ago. These icy bodies brought water and also organic molecules, the building blocks of life. The water condensed, forming oceans. The organic molecules may have contributed to the chemistry that eventually led to life. This idea that the ingredients for life came from space is both humbling and astonishing. The water you drink, the ocean you swim in, may have once been frozen in a comet, hurtling through the darkness before crashing into the young Earth. We are made, in part, from the debris of the solar system. Salt deposits form when ancient seas evaporate. In some places, you can find thick layers of rock salt, halite, buried underground or exposed in cliffs. These deposits formed when shallow seas evaporated under a hot sun. As the water disappeared, the dissolved salt crystallized, forming beds that could be hundreds of feet thick. Sometimes these seas refilled and evaporated again, creating multiple layers. The salt mines of Poland, the Bonneville salt flats in Utah, and the Dead Sea are all connected to ancient evaporation. Salt deposits are valuable. They have been mined for thousands of years for food preservation, industry, and chemistry. They are also geological indicators, telling us that the region was once covered by water, that the climate was arid, and that the land has undergone dramatic changes. Salt is a memory of vanished seas, left behind like a signature, a reminder that even oceans are temporary. Oil and gas deposits are found in sedimentary basins. Fossil fuels do not form everywhere. They require specific conditions. Thick layers of sediment, rich in organic material, buried and heated to just the right temperature over millions of years. These conditions are most commonly met in sedimentary basins, low-lying areas where sediments accumulate. Ancient river deltas, shallow seas, and swamps are ideal. The Persian Gulf, the Gulf of Mexico, and the North Sea are all sedimentary basins with vast oil and gas reserves. When searching for oil, geologists look for these basins, study the rock layers, and identify structures where hydrocarbons might be trapped. Finding oil is an exercise in reading Earth's history, understanding where ancient life flourished, where sediments accumulated, and how tectonic forces shape the land. It is a reminder that the energy powering modern civilization comes from the geological past, from life and landscapes that no longer exist. Natural gas is often found alongside oil deposits. In the same sedimentary basins where oil forms, natural gas also accumulates. Both are hydrocarbons, formed from the remains of ancient organisms. The difference is mainly in molecular size and the conditions under which they formed. Oil forms at moderate temperatures and depths. At higher temperatures and greater depths, the organic material breaks down further into simpler molecules: methane, ethane, propane. This is natural gas. It is lighter than oil, so it often accumulates in the highest parts of underground reservoirs, forming a gas cap above the oil. Sometimes gas is found alone, in reservoirs too hot or deep for oil to form. Natural gas is a cleaner burning fossil fuel than coal or oil, but it is still finite, still a product of ancient geology. Like oil, it is a gift from deep time, stored in rock, waiting to be discovered and released. Some deserts are filled with ancient sand from long-gone seas. The deserts of today were not always deserts. The Sahara, the largest hot desert in the world, was once a lush green landscape with rivers, lakes, and forests. Rock art and fossils tell of elephants, hippos, and crocodiles. As the climate changed, the region dried, and sand replaced vegetation. The sand itself is often ancient, grains of quartz weathered from distant mountains, carried by wind and water over millions of years. Some desert sands were once part of ancient riverbeds or coastal dunes from seas long vanished. Deserts are not barren wastelands. They are palimpsests, landscapes where past and present overlap, where the wind reveals fossils of ancient life, and where the sand itself is a story of erosion and transport across deep time. Fjords were carved by glaciers during the Ice Age. The deep, narrow inlets that cut into the coasts of Norway, Greenland, and Alaska are called fjords. They were carved by glaciers during the last Ice Age. As massive ice sheets flowed down valleys toward the sea, they eroded the bedrock beneath them, deepening and widening the valleys into steep-sided troughs. When the glaciers retreated and sea levels rose, the ocean flooded these U-shaped valleys, creating fjords. The walls of fjords were often sheer cliffs, thousands of feet high, plunging into deep water. Fjords are among the most dramatic landscapes on Earth, testament to the erosive power of ice. They are relics of a colder world, carved in ice, and now filled with water, quiet and timeless, reflecting the sky. Loess is wind-blown silt deposited over thousands of years. In some parts of the world, especially in China, the central United States, and parts of Europe, thick deposits of fine-grained sediment blanket the landscape. This sediment, called loess, was deposited by wind over thousands of years. During the Ice Ages, glaciers ground rock into fine powder. When the glaciers retreated, winds picked up this dust and carried it vast distances, depositing it in layers that could be hundreds of feet thick. Loess is extremely fertile, making it ideal for agriculture. The Great Plains of the United States and the farmlands of China owe much of their productivity to loess. It is soft and easily eroded, which is why regions with thick loess often have deeply incised valleys and dramatic landscapes. Loess is a gift from the glaciers, ground and carried by ice and wind, settled gently to become the foundation of farmland and civilization. And now, as the final fact settles softly into place, let the weight of deep time hold you gently. Tonight, we have journeyed through stone and fire, through the slow dance of continents and the patient carving of water. We have seen mountains rise and fall, oceans open and close, life appear and vanish and return again. Geology is not just the study of rocks, it is the study of change, of transformation, of the endless cycles that shape the world. The ground beneath you is not solid and unchanging. It is alive, in its own slow way, breathing through volcanoes, shifting through earthquakes, sculpting itself through erosion. You are standing on a surface that has been ocean floor and mountain peak, desert and forest, ice and fire. The rocks remember all of it. And in remembering, they tell us who we are. Brief visitors on a planet far older and grander than we can comprehend. So rest now. Let your thoughts drift like sediment settling on a riverbed. Let the ancient rhythms of the earth calm your mind. Somewhere tonight, a volcano is quietly building. A river is carving a new valley. A crystal is forming in the dark. The planet continues its work, patient and unhurried, as it has for billions of years. You are part of this story too, made of the same elements, shaped by the same forces. Sleep well, and thank you for dreaming with us.